Alright, so for all the topic 2 stuff, which is your inorganic chemistry, there's only 2 units you're going to need to know about. So the first one I'm going to talk about is acids, alkalis, and titrations. So these are just the spec points that you need to know, obviously. And then the first one's quite easy. It's just the different indicators you can use. So I'm going to start with 2.29 because that just makes it a lot easier to start with. So that's your pH scale, right? And then your 0 to 14, and these are your acids, and these are your alkalis. And at 7, that's your neutral pH. So that's just not an acid, not alkali, it's in between, yeah? So over here are your really strong acids, and here are your strong alkalis at the extremes. And then as you go here, it's like a weak acid. And that's around, according to the spec, obviously 4 to 6. And here your weak alkalis. And these are from 8 to 10. Okay, so that's just your pH scale. Sorry, that should be a small p. Not quite sure why, but that's what it is. And now if we look at indicators, so there's the 3 indicators you need to know about, which is litmus, and this can be a paper, or it can be a solution. Normally we use litmus paper, so in class you probably have it as like that small strip of paper, and it can be red or blue. So litmus with acids will be red, and with alkalis it will go blue or purple, but I would say blue. And the next indicator is phenolphthalein, and that's just horrible to spell, so I'm not even gonna try. I'm just gonna call it P. So this only has 2 colors as well. So in an acid, it is colorless, and in alkalis, it is pink. And the next one is methyl orange, and the easy way for me to remember this is, so it's orange when it's neutral, and then when it becomes an acid, it goes red, if I can spell red correctly, and in alkali, it goes yellow. So the way I can remember this is with litmus, I know it goes red in acid, and because it's methyl orange, and orange is the neutral color, so if red's on one side, it has to be yellow on the other, because you know the color wheel, red and yellow make orange, and that's how I remember this one. So our next spec point, which is universal indicators to measure the approximate pH values. So basically all it is just like, so universal indicator, it's just like a solution. You put a couple drops of it into like a solution to test the pH basically. And neutral, it's green, and it's basically like the rainbow. So it's like red, orange, yellow, green, blue, indigo, violet. So if you haven't redone it in physics, it's Roy G. Biv, R for red, O for orange, etc., etc. And so you kind of just sub the colors of the rainbow in. So with red being your acid, and purple or violet or whatever you want to call it is your alkali. And you should remember it's neutral when it's green. So normally when you have the indicator like in like your lab or whatever, right? So you have it in like a green bottle, not a green bottle, but the solution will be green in the bottle. You know what I mean? And that's the neutral one. You drop it in, and then it will change color to match. Like if it's an acidic solution, it will go red. If it's alkaline, it will go violet. That's if it's like really strongly acidic or alkaline. You know what I mean? So the next ones are acids and aqueous solutions are a source of hydrogen ions, and alkalis and an aqueous are a source of hydroxide. Wait, let me just clear some of this out. Actually, we'll go down here. Okay, so basically, one way you can learn about acids and alkalis are that acids are proton donors. Oh wait, this is the wrong thing. That's the next point. This one is acids are H+, yeah, hydrogen ions. So, I'll make a video of ions later. It should be ahead actually, so yeah, the ions part, it's already there, but, so an ion is just a charged particle, and hydrogen is positively charged, and that's your H+ ion, so that's a hydrogen ion, and acids just give H+ ions off when they dissociate in water. So for instance, most of us know hydrochloric acid, that's hydrochloric, yep, so that's HCl, right? But if you put that in water, so an acid's just a solution, basically it's aqueous. So it'll be AQ, it dissociates in water, so it splits up into like the 2 ions that make it up, and that goes in H+ and Cl. And then the thing about acids that make them special is that they all have a H plus ion. So that's annoying. Okay, let's say we have H2SO4, which is sulfuric acid, right? And so ignore the fact there's a 2, because that really doesn't matter. That just dissociates into ions as well. So that goes into 2 H plus ions, because you have 2 there, and an SO4 2 minus ion. And for another acid, another one we'll have done in labs is nitric acid. That's HNO3, and that also goes into H plus and NO3 minus. And the thing that they all have in common is the H plus ion, which makes them acids. And for alkalis, it's a similar thing. Alkalis all have an OH minus, and that's just what makes them an alkali. So I know this unit's been removed from like the advanced information or whatever, but if you remember when you did group 1 metals, like so if you put like lithium in water, right, in water, you get LiOH, which is lithium hydroxide, and H2, which is the gas. And just balancing that equation quickly, it should give you this, right? And this is an alkali or a base or whatever you want to call it. And the thing that makes it a base or an alkali is the OH minus ion in it. That's why, you know, if you have, in the case it turns purple when you have this experiment. So that's points 2.31, 2.32. This is quite a simple one. It's just, you know, alkalis neutralize acids. That's just what they do. And the next point, to carry out acid-alkali titrations, I will explain in this separate clip. Alright, and to save you from my artistic skills, I've pulled up a diagram of acid-alkali titrations, and I'm just going to walk through it really quickly. So the first thing you do is you have a pipette and a pipette filler, and that's not how you spell filler at all. There we go. And a pipette filler is not on this diagram for some reason, but it's basically just like some rubber thing that you squeeze as some valves on it. Yeah, I'm not going to try and draw it. Basically, you squeeze in it, and then it like creates pressure, vacuum, I don't know, physics. And it sucks up the liquid from the solution into the pipette. And then you can drop it in this conical flask over here. And it's a lot easier to use like a measuring cylinder or whatever, because pipettes are a real pain to use. But the reason we use it is because it's really accurate. So you want 25 cm cubed because it gives you accuracy, and you need it to be accurate. So you use a pipette because it's calibrated and everything, and a measuring cylinder is not. So you put it in your flask, and then basically the point of the titration is to find the amount of, so in this case you have your acid, right, and you want to find the amount of alkali, which in this case is sodium hydroxide, that you need to neutralize the acid. Okay, so you have your fixed volume of hydrochloric acid, and we're finding out the volume of sodium hydroxide you need to neutralize it. So what we do is we put the sodium hydroxide in a burette, which is that really long, like, glass tube, and it has a tap over here. And something very important is you need to record it to 2 decimal places. And I know I promised we're not going to have bad drawings by me, but I lied. So what they mean by that is, let's say we had this. Give me a second to draw some lines. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so let's say that's 20 and that's 21. It doesn't really matter, but it's just for the point, I guess. So this would obviously be 20.10. Well, not obviously, because normally you just write 20.1, right? Because you need it to 2 decimal places, it always has to be 10. And this would be 20.20, etc., etc. And let's say this is the level of your liquid, right? So if it was here, you would just say 20.1. Pretend it's on the blue line. I'm just not very good at this. And the difference is, let's say you had a line here. So this would obviously be 20.40, and that's 20.50, right? And that's in between, so you would do 20.45. But let's say your line was really, really close over here. So it's almost 20.20, yeah? It's almost there. But you can't say it's 20.19 or like 20.18, because that's just not very accurate, I guess, and it's just too subjective. So instead, we would always say that's 20.15. Because, yeah, it looks a lot more like 20.19, right? But that's just not what we do. We always do it to the nearest 0.05, sorry. So that's what they mean by 2 decimal places. Anyway, so after that, let's change back to a color you can actually see, which is blue. And so after you put that in, you add some indicator. And this is indicator we were just talking about, phenolphthalein. And as we remember, it's colorless in acids and pink in alkalis. And since we put our hydrochloric acid in the pipette and it's a conical flask over here, it should be colorless because it's an acid, right? So there's no effect when you just put a couple drops in, because then you're going to add in your NaOH slowly until it changes color. So you turn open the tap and then you just like let it out until eventually it changes color. So you need to make sure you're swirling this conical flask as you're doing it, and as soon as you see it turn pink, which means alkali, so that's the point of neutralization. And then you read off your burette again, make sure it's to 2dp. Remember this diagram over here, which I hope makes sense. And then this pink because it's alkali now, so that's your neutralization point. And then you know that that's the amount of NaOH you need to neutralize 25 HCl. So basically what you do is you take your final reading on the burette, and then you minus it by the initial reading, and that is the volume of NaOH needed to neutralize 25 cm cubed of HCl. You could do it the other way, so you could put your NaOH in the pipette into the conical flask, and then measure the amount of HCl needed to neutralize it. It doesn't really matter, but that's just the principle of acid-alkali titrations. Alright, and the only other thing you need to know in topic 2 in organic chemistry is acids, bases, and salt preparations. So this ties in quite nicely to the titration thing we were just talking about. First, let's just quickly talk about solubility rules. This is one of the really annoying things in the course. You just have to memorize them. Solubility rules. Okay, so what you can see up there, but basically, the way I remember it is with tables. So then you have your soluble stuff over here and your insoluble stuff over here. So all your sodium compounds, your potassium, why am I doing in ions? I don't know what I'm doing anymore. Sodium ions, potassium, and ammonium are soluble, like no matter what. So it could be sodium chloride, which is normal salt, which is soluble. Or it can be potassium iodide, anything, as long as it just starts with one of these, it's always soluble, right? And all nitrates are soluble as well. So then NO3. So anything that ends with NO3. So for instance, you could have I don't know, sodium nitrate, and that is soluble. No matter what, it's always soluble. And then the next rules are like, they say it's soluble, but there's some like what's the word for it? Oh my god. Exceptions, there we go. So then your chlorides are soluble. So over the Cl. So for instance, well, we just talked about sodium chloride, but any other chloride, so magnesium chloride would be soluble, for instance. But apart from silver and lead. So you just need to remember those two rules, because normally there'll be a lake. So let's say there's a precipitate. If you mix two solutions and you get, I don't know, you get silver chloride, you have to be like, that's a precipitate because it's insoluble. And for the next one, it's similar. It's all sulfates, except for barium, calcium, and lead. You just need to memorize this again. Let's extend that column. And then you have all your carbonates, which are insoluble this time. So any carbonate that's insoluble, except from sodium, potassium, and ammonium. And that's just, you just need to remember these are always soluble no matter what. I'm just drawing an arrow there. And hydroxides, which are your OHs, are all insoluble as well, apart from those ones. And also calcium, because calcium hydroxide is slightly soluble. Okay, so those are just the rules, you need to memorize them. And next, acids and bases in terms of proton transfer. Okay, so you just need to remember this one as well. Acids are proton donors. And then alkalis are proton receivers. Okay, so remember when we said acids dissociate into H plus and something else, right? And your H plus ion is just a proton, because normally hydrogen is, if that's your electron shell, right? And that's your nucleus. There's just one proton inside, and then there's your one electron. Then if you lose the electron to make an ion, to make it H plus, it's literally just your nucleus, which is just a proton. So your H plus is a proton, so that's why acids are proton donors. and alkalis or bases, bases, not alkalis, are proton receivers. Let's just check those bases. Oh, okay, proton acceptors, same difference. Okay, so basically that means they take the H plus. So you know when acids and bases react, you get a neutralization reaction, which is just water and salt, right? So let's just do this. So remember, all alkalis and bases are OH minus, and all acids were H plus from the previous thing. And basically your base accepts a proton, so they react, and you get H2O, and then you get a salt as well. But we're just talking about like the important things now because this is general. If I gave an example, we could have HCl plus sodium chloride, because that's what I've been talking about a lot for some reason. So in here, you know neutralization gives you your salt and water, right? So you get H2O because this is happening there, as you can see, give you H2O, and then you get NaCl, which is your salt. That just varies, obviously, depending on the acids and the bases involved. Okay, so your next point. Oh wait, these two were basically what I was just talking about. And so the reactions of acids with metals. Okay, so this one's just about knowing like the general formulas and everything as well. So, what do we need? Acids with metals, bases, and metal carbonates. Okay. Okay, so first let's start with metals. I have written everything I need to write, right? Metals, bases, metal carbonates. Okay, perfect. So first, let's start with metals, obviously. So the general thing for this is acid plus metal makes salt plus hydrogen. So an example of this, let's stick with HCl, and let's say magnesium, right? So your salt is magnesium chloride, and your gas would be hydrogen. And now we need to balance the equation, so your 2H is over here, so add that. And that's perfectly balanced because you have 2H and 2Cl, and H2, Cl2, and Mg. So that's for metals. And that's the same for like another acid. Let's do sulfuric acid, which is H2SO4, and let's react with sodium. So you get sodium sulfate, and that's to be Na2 because 2 minus charges plus H2. And that is balanced now if I add that, I believe. Okay, so next is with bases. So as an example of a base, we need general formula first. So in the base, I would normally talk about metal hydroxides. So now we need acid plus metal hydroxide, and this gives you water and a salt. So, I forgot to mention, so basically a salt, right? Obviously you think of a table salt, but in this context, you just get the metal, so like magnesium, and then you add like second part of your acid. So if it's hydrochloric acid, it's something chloride. If it's nitric acid, it's something nitrate. If it's sulfuric acid, it's something sulfate. And this something obviously is just your metal. So to like make that a bit more obvious, let's do an example for bases. Let's say you have hydrochloric acid and you react it with sodium hydroxide. Okay? And then so water, which is just H2O obviously, and your salt will be the metal, so sodium, and then chloride, because that's hydrochloric acid. And I believe that's balanced. Yeah, that's balanced, which is nice. Let's do another example. We haven't done nitric acid yet, so let's do a nitric acid example. I'm gonna just react that with sodium hydroxide as well, because that's just easy. So then H2O, which is your water forms once again. And so remember the salt, first part is the metal, so sodium. And since it's nitric acid, it makes a nitrate. Okay, so the final thing you need to know about is metal carbonates. And so the general one for this is acid plus metal carbonate makes carbon dioxide. And you can remember that because carbonate's carbon dioxide, same thing. Well, same thing, but it sounds similar. Water and then salt. Right, so let's go back to my favorite example of hydrochloric acid. And let's react that with calcium carbonate. So you get CO2, and then you get H2O, and that's just your generic ones, I guess. And then salt. So then once again, get your metal, which is calcium, and HCl, so it's a chloride. And now we need to balance. So I believe that is now balanced. Yep, that's balanced. Alright, so your next spec point, which you need to know about, is to know that metal oxides, metal hydroxides, and ammonia can act as bases, and that alkalis are bases and soluble in water. Well, I mean, I've kind of already done that when I basically just assumed for you that bases are metal hydroxides. Well, I mean, yeah, let's go with a metal oxide as well. Just to show you that bases are metal oxides. And we'll do an ammonia example. Let me just move that down as well. So you can do ammonia just to like reinforce, I guess. Those are bases too. Okay, so metal oxide and ammonia. So for metal oxide, it's acid plus that makes water and salt as well. So let's do magnesium oxide plus, let's change it up and do sulfuric acid again. So that makes water, which is H2O, plus MgSO4, which is your salt. So it's basically just the same thing, it's just you're using a different base, but it does not matter at all. Ammonia. So ammonia is NH3, that's different from ammonium. Sorry, this is a bit of a sidetrack, but ammonium is NH4, and it's an ion, so it's a plus. Alright, so there's a slight difference with the ammonia one. So instead of making water and a salt, whatever, you will just make your salt. So ammonia, so that's okay. Acid plus ammonia makes salt. So for example, let's pull out hydrochloric acid again. So in hydrochloric acid plus ammonia. So remember ammonium, you'll make ammonium chloride. So then that H goes there, so ammonium, and then chloride, you just add your Cl. Right, so now we're going to talk about your salt preparations, which you need to know, and these are really easy to mix up, so make sure you know them well, because they give you loads of marks in exams. Like, they normally go for 6 marks-ish, and obviously they're in green, so you're going to get them. So let's, oh yeah, I pulled up diagrams to save my exams, by the way, so credits to them, just to save you from a lack of artistry. So the first one we're going to talk about is this one, which is making a soluble salt, starting from insoluble reactant. So, a common one, so that's also going to be covering practical, 2.42, and that's making copper sulfate. So I'm just going to call it that, because I'm not writing the whole thing out. Making copper sulfate. Okay. So, your first step is to heat an acid, normally with a Bunsen until it warms up, and that's to increase the rate of reaction. Because basically what you're doing here is you have your insoluble metal base, carbonate, whatever, and so obviously we're making CuSO4, that will be copper carbonate. And then that means your acid is H2SO4, because remember, if you're making this as your salt, you need the metal, and it has to be sulfuric acid because you're making it sulfate. So then basically you heat up your acid, and that increases the rate of reaction, so your copper carbonate will dissolve quicker and react faster. And the point of this is to make your CuSO4, because it reacts and makes that. And then your next step is to filter out, because what you're going to do is you're going to add this until excess. So until it's an excess, and that means all your acid will react. So then you will have CuCO3 as like an excess product, as well as your salt, which is CuSO4. So then you filter it out to get rid of like get rid of all this excess, basically, because you want your CuSO4, which is going to be a liquid. So then up here, your excess CuCO3, which is your copper carbonate, is your residue, and then your filtrate will be CuSO4, copper sulfate. And then to use filter paper, filter funnel, obviously, and then you transfer it to an evaporating basin. And now what you're going to do is heat it up. But you're not going to heat it until all the water goes away. You're just going to heat it until some water goes away or evaporates. It's really important you say some, because that's what the mark schemes want, and if not, you're going to get reject your marks if you say all water disappears or whatever. Or you could say until crystals start to form. And then after that, you get your crystals which start forming, and you take it off the heat. And after that, you let it cool down, so your crystals fully form. And once it's cool, you want to dry it. So you can either pass it dry with filter paper, or you can use a desiccator, which just dries it. It's like a drying oven. Or you can leave it in a warm place, but that normally doesn't give you marks, so don't write that. Okay, so that's your first one, which is making a soluble salt from an insoluble substance. So your next one is your titration, which we've basically already gone through, so I'm just going to skim over this really quickly. So this is when you get acids, alkali, you neutralize them, and then you get your salt. Okay, so first you do the normal titration, which we talked about, and you use an indicator. But then, now you know the volumes to neutralize it, right? So you find out the volumes of acid and alkali to neutralize. And then, because here you've done it with your indicator, right? But you want it to be a pure salt. So then you can't have your indicator, because your indicator will contaminate it. So you repeat it with the correct volumes you found, because now you know the volumes, right? So you repeat with those volumes, but without your indicator. Alright, so after doing that, you get your salt. And it's basically the same as previously, you just heat it up until some water disappears. All crystals start to form. I'm not going to write that because it'll take too much time. And then you just dry it with a desiccator, or what's its face, or with filter paper. So your third type of salt preparations is the precipitation method. So this is why I was talking about learning which salts are soluble and insoluble earlier, because this comes out and it's really useful to know. So this is when you have two soluble salts and then you make an insoluble. So I know we're calling them salts, and normally think of salts like little granules because that's the salt we have, right? But because it's soluble, you have to dissolve them and it's just the solution. And the example we normally do for this one, if we go back up to the spec, is lead sulfate. And so what you do is you need lead and sulfate. So you need sulfuric acid, which is H2SO4. And you just need a soluble lead compound. So let's go with, if you go up to your table again, right? This is why I was talking about it, because we know all sulfates are soluble except from lead sulfate, which is insoluble, which is why you can make it with this method. So let's say we're doing lead chloride. As our other solution. And so you mix your two soluble solutions together, you give them a stir, and it will form your insoluble lead sulfate, which is what we want. And then because it's insoluble, we can filter it out. And it's the residue, because it's insoluble, so it doesn't pass in the filter paper. And even if we're calling it the residue, it's actually what we want. So this is the salt we want. And then we need to make sure it's a pure sample. So what we're going to do after this is, because that is our lead sulfate, but there's also going to be a little bit of the two solutions left over. So some of your lead chloride or some of your hot sulfuric acid, which is still going to be there. So what we do is we wash it with deionized or distilled water. And it's important it's specifically deionized or distilled, because that means there's no ions to contaminate it, which is the whole point of us washing it in the first place. So you wash it, and then you have your pure crystals. But they're wet, and we don't want them to be wet, we want them to be dry. And the way we're going to dry them is put them in a desiccator or pat them dry with filter paper. And that's basically all you need to know for this whole unit.